So let's get this started. Hello, welcome. We have a special guest speaker at the beginning of class today. This is Kayla, who is a
Non-physics, or I'm a senior.
You're senior. Time flies. It seems like only yesterday you were taking the class.
Oh, I know, it's a blast.
Anyway, Kayla has a short announcement, so I will let her take the floor.
All right, hi guys. As you can probably tell, I'm one of the students who's running the peer mentoring program for physics. It's geared towards physics majors, and so what would happen is sophomores and freshmen would be paired with either a junior or senior to kind of get light peer mentoring. So it'll tell you, they can help you decide what classes you want to take next year. You guys are going to be going up to the 300s. Woo! It's a wild time. It's a good one though. It's also meant for you guys to meet some upperclassmen. I mean, I don't know you guys' friendship status, but I don't know most of you guys. That's kind of sad to me. So I know some of you guys though. So how many of you guys are doing mentoring right now? You guys are my mentees. Oh, yes. So I highly recommend it. I've done it since my freshman year, and it has certainly helped me stay in the program and succeed in the program. You guys want to say anything about it? Not to put you on the spot, but, you know. All right, well, that's my plug. So an email was sent out with the form that you can fill out. If you can't find it, you can email either me or Dom. I think that's it. Are there any questions?
Cool. Awesome. It's a talkative group. You have to just shut them down all the time. Just keep yapping and yapping and yapping. Oh, there's a question.
Yeah, but is like your mentor program like set times or set dates?
Oh, yes, perfect. I forgot to cover that. No, so it'll be about an hour a week with your mentor. You can choose day, time, everything. It's just up to you guys. There isn't a set time. I know a lot of people say if you guys felt like you didn't need a whole lot, you could be like, every other week you meet. It really just kind of turns out into a hangout sesh. It's a great time.
Excellent question. Any other questions? I will say, good.
How are you assigned mentor?
So I just kind of do it. So I have a Google Sheets because I share it with someone. Trash time, Excel is superior. But, and I just match it with people. So you'll write a response and I'll try to kind of pair up if the mentor and mentee kind of have the same sort of give and take they want. So like say if you're like, I really want to know about more classes, and a mentor is like, I would love to tell someone about classes. And if it ended up being where you didn't get along with your mentor, you can email me or Dom, and we can just put you with a new one. It's not a problem.
Awesome. I will say in a semester of total weirdness and unusuals and lack of personal contact and social interaction, this is probably a pretty good way to at least facilitate some of that, at least somewhat naturally.
Yeah.
Yep. All good things. Thanks, Gail.
Yeah, thank you.
You can take her info and Dom's info, send them emails if you have other questions. But thanks for stopping by. Good job, Kayla. Woo! Good stuff. Okay. Where were we? We were talking about fluids. Let me get an attendance thing up here real quick. 4099. Oh, right. Announcements. There is, I forgot to mention last time, I did post a capo over the weekend, on Monday, I can't remember. I think it was Monday. It is not due this week. We haven't even covered really any equations or physics yet associated with fluids. So having one due tomorrow will be a little more future. It will be due tomorrow at the usual time, Thursday evening. We should be done certainly by tomorrow, by Friday, with everything you're going to need for that proposal. So you can look forward to that. Okay, so we did some preliminaries. We talked about what fluids are. We talked about some different ways we're going to think about fluids in continuum mechanics as opposed to point particle mechanics. Let us actually start doing some physics. And we're going to start our physics with this physics of statics. So let's bring this slide up. This is a picture, a diagram from Halliday, Resnick, and Walker. We're moving back to chapter 14 in that thing. One of the ones you skipped in N11, going back and reading that one now. That's the fluid chapter. Okay. So here's a situation. We want to know for a statics case. We've just got fluid, water, let's say, in a tub or in a cup or in anything else you might want to know. What can we say about the fluid just sitting there? There's actually quite a lot you can say about static fluids. So let's start with considering a volume element within that fluid. This volume element could be a rectangular cube or some sort of rectangular region that has some area and some depth, difference in y between the top of it and the bottom of it. Okay. Okay, let's go to notebook. Let's start writing some stuff. We have control today. It's a good day. Okay, statics. Or let's just be more specific, static fluids. Okay, so this is the situation we've got. We've got some sort of container, and that container has some sort of fluid in it. And let us consider some sort of region, three-dimensional region inside. I should just draw this probably. But this isn't, there's no object in here. This is just a section of the fluid inside the fluid. Okay? So, that fluid sitting in that container is not accelerating in any direction. The net forces on that volume element of fluid must be zero. Can we all agree on that? Okay. So, A is zero. So the net force acting on that fluid volume region must also be zero. That's not to say the pressure is zero, because it's not. There's always pressure being applied by these fluids. But it is to say that the net force, you take the force acting on every single one of the sides of the fluid element that we're considering, must be zero. Okay? Okay, so let's consider the forces that are actually at play on this fluid element. We know what are these forces? Let's write them down and be specific. We know that there is a force pushing upward on this from below due to pressure. The fluid elements just below our region have a pressure, and they will be pushing up on this particular region. Let's call this F2. And let's call F1 the force pushing downward from above. And let's call that F1. This one, the force from the water above it is pointing down. The force from the water below it is pointing up. Right? So we've got force, water on top, pushing down, force of the water on the bottom, pushing up. There's one more force we need to consider for this volume element. What is that? The side. Yeah, that's true. I'm sort of not going to be worried about the size too much. Let's think about why we're not worried about the size too much. We know that whatever force is pushing this way has to equal the force pushing this way, and there isn't any other forces to worry about. So I can actually ignore the size and avoid ignoring the size. I'm mostly interested in the top and the bottom. But there's another important force that either points up or down that is connected to this particular volume.
Would it be like the gravitational force?
That's right, the gravitational force itself. This fluid is all in the gravitational field. And so you've got some force pushing down, up from below, some down from above, and you also have the gravitational force of the volume element itself in the fluid that will be pushing down. So, also, you have a force due to gravity. What is that force of gravity? In the simplest terms, it's mg. The mass of that, whatever volume of fluid you have, times g acceleration due to gravity. And it's in the downward direction. Okay, we know that this fluid is not moving. We know that the acceleration these forces have, and again, that was a good point about the sides. I don't really care about the sides because I know that there's no other real forces to worry about. I'm not learning anything really by thinking about the sides. I'm really thinking about the top and the bottom because that's where there has to be a difference, and we can quantify what that difference is. Okay, so the fluid is not moving, so all forces must balance to 0. So we have the downward F1 plus the upward F2 plus the downward Fg must add to 0 in the vector forms. Since these vectors are all pointing parallel or anti-parallel, we can just take the magnitudes of these vectors and think only about the magnitude of these vectors, and that will make our life a little easier. We can say the magnitude of F2, the only upward force pointing one, has to equal the magnitude of F1 plus the magnitude of F2, the two downward facing ones. And then we can just treat all these as positive numbers and make it a little simpler. F2, we just think about these as magnitudes, is F1 plus mg. And there is a good formula for us. Except we're not really interested in total forces, and we're not really interested in total masses. Let's see if we can take this from an equation that looks very much like our AMA 1 and turn it into an equation that's much more continual mechanics. So first of all, we don't really want to talk about forces. We want to talk about pressures. So let's divide through by area, and that will turn all those forces into areas, into pressures. Which area are we talking about here? What is this A?
It's the area of the top and bottom. So these are acting just for.
Right. We're talking about, well, if we want to, we can divide by any area we want to. There's really no limit on what area. What we want to use is an area that will turn that force into a pressure. And that force becomes a pressure if we take the total force on an area and divide by the area of that, area. And so the area must be the surface area of the top of whatever fluid element we just defined. And hopefully, if we've done this in the same way, that will be the same as the surface area on the bottom. That's the area of top and bottom. Okay, that makes this become the pressure P2, which is the pressure on the bottom, corresponding to F2, is equal to the pressure at the top plus mg over A. Already, we know that mg over A has to be a positive number. So already we have shown that the pressure at the bottom of this fluid element has to be higher than the pressure at the top of the fluid. It's just a natural consequence of fluids acting in a gravitational field. The pressure has to go up as you go down inside. In fact, it is that change in pressure that holds the fluid up. If there were not a change in pressure, those forces wouldn't balance and you would have the pressure fluid moving up. Okay. Okay, we're almost there. We've got pressure, but we don't want masses, we really want volumes. So we want densities. We need to turn our mass into a density, because we don't really care about the individual fluid element we've chosen, we care about the properties of the fluid itself. So, we know that we want to turn this mass into a density. We know that density is equal to mass divided by volume. What is the volume of our unit of our fluid element? Well, we know we've got it's the volume of the cube. Okay, in terms of we're already using A, the surface area at the top. In terms of the surface area at the top and the bottom, what would this be? Let's actually put that right in there. H. What is H? Let's call that somehow a delta Y. Okay? H delta Y, sort of the same thing, except we're going to define H in a slightly different way later. Delta Y is simply the difference in Y position between this point and this point. So this has surface area A, and it's got depth delta Y. A times delta Y will give you the volume of that fluid element. Great, so mass, solve this for mass, is density times volume. We know density, this is equal to density times area times delta Y. Plug this in for mass, and we get this. We get that P2 is equal to P1 plus rho times G times A times delta Y divided by A. And look at that. Those A's just go away. We don't even really care how big a fluid element we've defined. The A's disappear. And that's really what we're going for. And now we've got properties of the fluid itself without having any properties left of the volume element that we actually chose. Let's write this a little bit differently. P2 equals P1 plus rho times G times delta Y. And that can have a box. Does it matter if we chose a different fluid element? It does not. Any fluid element we choose, the only thing that's going to matter in defining what the pressure is at the top of that fluid element and the pressure at the top of that fluid element is the change in elevation against the gravitational field of those 2 points of the fluid. So we can immediately track the depth of pressure as a function of depth. It only depends on the density of the fluid that we're talking about. Right, so right. The density of the fluid is the only remaining variable in this equation. If your fluid is incompressible. We're assuming that the density is not changing, therefore, and that's the assumption that we've made here. But even, I assume this works also if the density is changing, you're just going to need a more complicated way to solve for the equation. We're going to only be considering cases where the density is constant. Okay, so other ways to think about this. P2 minus P1, the difference in pressure, is rho G delta Y. Sometimes you'll see this as delta P equals rho g delta y. The change in pressure, density times acceleration due to gravity times change in pressure. Note that this gets a little bit confusing because people will often use H, and we're going to write this equation a little bit differently in terms of H. H and delta y are not the same thing. H, let's write it in another way, and then let's talk about how these are different. This is also sometimes the way people will write this equation. The pressure equals P0 plus rho GH. Right? This is basically the same equation, but it's making a couple of changes to how we're thinking about this. Here, H is the depth below the surface. And P0 is the pressure at the surface. Which is almost always atmospheric pressure. So the pressure at the surface is not zero. Why? Because there's air pushing down. If you're at sea level, that's 1 atmosphere. Right? So it goes up from there as you go down. Now this is a very different way of defining the delta y. How are H and delta y different? There's two main ways. One is delta y is simply a difference in y position between any 2 points in the fluid, and H specifically refers to the surface and a point below from the surface. The other way, and this is where people get confused on this the most often, H is always a positive number and increases as you go down. Delta y increases going up. Delta y is a difference in height between two regions in the fluid. So there can be a negative sign difference between H and delta y that you have to worry about and think about. H is always a positive number. Delta y is always a positive number, but they're actually counting in different ways. So be aware of that. Okay. So let's do an example.
Quick question on that.
Yep.
Is it correct to think of H and delta y terms as like y1? If you had, if you have y2 minus y1, y2 would correspond to your local point, and so y1 would just simply be a y equals 0.
That's right. It's the same equation, really.
So that's where you're thinking increasing.
Well,
y2 is deeper.
It's almost that, right? So you get this equation from this equation by setting y1 to 0, and then setting delta y to negative h. Right? Because P2 is the pressure at the bottom, and P1 is the pressure at the top. We've switched those here. P0 is the pressure at the top, and P is the pressure at the bottom. We've really switched the sign there. Right? This is really P2, and this is really P1. This delta y right, so go ahead.
The delta y would be, so to find P1, you could use the delta H equation. You find P1 at, let's say, like a meter below the surface.
Right.
And then P2, you could say, well, the delta y is you go down another half meter.
Right.
In reality, you could say you could find P that we can also find P2 that way, but then you go down 1.5 meters instead. And that's where you find the difference. And is that what you're saying? You're doing like the increase? If you're
Let me-
finding P2
Let me say this. This delta P, delta Y, you always have to know that your delta Y is going to be positive and your P is going to be larger at the smaller value, at the lower value of Y, right? So you sort of have to know that sign going into it. You have to know how that delta P works. You have to know that it's higher the lower you go, right? And so in that case, you don't have to worry about the signs too much because there will be a positive delta Y and a positive delta P. You just have to know that the top is lower and that delta, how that delta P works on the thing. This thing, these numbers should all work. These numbers are all positive, right? This is always the one below the surface. This is always the one at the surface. So there's some signs you have to worry about in this one that you don't have to worry about in this one. I don't know if that answers the question.
I think it does.
Okay.
I don't know if I'm getting it in my head right.
Probably.
I'm not seeing where there's like a sign confusion delta Y.
Yeah, maybe there's,
Right now, I'm not seeing it. Maybe in like the example.
yeah. It's okay. If there's no sign confusion, don't be confused by the sign. But just be aware that that is the way these equations always have to work. The P, the higher P will be the lower value, will be the lower Y. Okay? And this H counts down from the top. Those are the things to be aware of as you're using these equations. Okay? Okay, let's do an example. Let's keep it on the football theme. If you're not a football fan, that's fine. This will be the last football example we do in the whole semester. But those of you who are familiar with this, it is apparently easier to kick a field goal in Denver, Colorado, which is a mile above sea level, than it is in San Diego, which is at sea level. Because the air is thinner, the pressure is thinner, it's easier for things to travel through. So the question is, how much thinner, how much less pressure is there at Denver, Colorado, 1 mile above sea level, than there is at sea level? What is the pressure difference between a city a mile high and a city at sea level? Between Denver and ocean. 1 mile above sea level. So we can use this delta P equals rho G delta Y. And we know all of these things. We know what density is. The density is going to be the density of air, 1.21 kilograms per cubic meter. Now, I'm making the assumption, which is wrong, that the density of air won't change as you go up. It actually does change, not insubstantially, as you go from sea level to a mile high. But let's just keep that constant to see what number we get. Let's say G, let's just round this off to 10 meters per second squared, if you're going to be okay with that. And let's say H is 1 mile high. Now, this is going to be, if you're typing this in your calculator, you have to do all kinds of unit conversions to get this to work. But I'm going to use a tool called Wolfram Alpha to do this for me. If you don't know about Wolfram Alpha, it's really useful. I just typed it wrong. This is sort of a baby Mathematica. If you know Mathematica, you can use Mathematica, and all of this Wolfram Alpha stuff is already built into Mathematica. But if you don't have Mathematica or you haven't learned Mathematica, this is a very easy, intuitive way to type things into in sort of natural language and have it do calculations for you and comparisons for you. So I can just type this in. I know I want to multiply the density times the gravity, acceleration due to gravity, times the height. So let's just do this. 1.21, and let's give it some, oh, that's right, kilograms per cubic meter. There's some units. I can multiply that by the acceleration due to gravity, 10 meters per second squared, and I can multiply that by 1 mile. And it will do all those unit conversions for me. I don't know if you can see this very well. Oh, that's better. Can you see that better now? Okay. So I just put in the units as I had them. It's going to analyze those things. It's going to multiply them together. It's going to convert them into units, and it's going to give us some answers. Let's see what happens. Internet connection is unstable. That's sad. So it gave me a result. 19,471 kilograms per cubic meter, or kilograms per meter second squared. $19,471. Let's actually round that up. We've rounded all this stuff. This is about 20,000. What were the units on, crazy units on this thing? Whoops. Oh, I pressed quit. That's not what I wanted to do. I wanted to tab. Kilogram per meter second squared. Is that what we expect? A kilogram per meter second squared? Is that a unit of pressure? What's pressure? Force per area. What's force? Newtons per meter squared. But a newton is a kilogram meter per second squared. So if you take a kilogram meter per second squared and divide it by meter squared, what do you get? Kilogram per meter per second squared. So, I think in fact, Wolfram Alpha knows what this is. This is a pressure. It knows it's a pressure. In fact, this is kind of some, it gives us some, let's compare. What is 20,000? This is actually 20,000 pascals. Pascal is a Newton per meter squared, which is equivalent to a kilogram per meter second squared. This is the typical air pressure drop in the funnel of a tornado. So I was going to add, the next question I was going to ask is this significant? The answer is, yeah, this is pretty significant. What percentage of the, what percent drop is this? Remember what the rough atmospheric pressure is in sea level? $100. So this is pretty easy. What's the percent? It's about 20% drop. This is 20% less. The air pressure in Denver is about 20% less than it is at sea level. That's a significant drop in pressure. That's noticeable. Walking around in Denver is different than walking around on sea level. The pressure is noticeably different. Let's just call this pascals. Come back to you. About a 20% change. So that's delta P. Again, that's delta P, and we know that it's going to be smaller at Denver, which is a higher altitude, than it will be at sea level, which has a lower altitude. Okay, here's another question. How deep in the ocean would you have to go to feel the same pressure change? Okay, so we've still got delta P equals rho G delta Y. Now we know what delta P and rho and G are. We want to solve for delta Y. It's a different rho, so we're not going to get a mile deep. It's going to be significantly less than that, but how much less than that? Let's solve this for delta Y. Rho G over delta P. And we can put that into Wolfram Alpha also. Oh, and we have a different density now. Let's say the density of water is about 1,000 kilograms per cubic meter. It's a little bit bigger for salt water, but this will work.
Can we tell me the
Yes.
okay, so we get the, delta P over.
Yeah, you're right. I did that wrong, didn't I? Haha. That's what I get for trying to jump ahead. Delta Y is definitely delta P over rho G. Better? Thank you. So let's take this 20,000 kilopascal, or 20 kPa, 20,000 pascals, and divide it by the density, which in this case is 1,000 kilograms per cubic meter, times 10 meters per second squared. That look good? Let's hit enter, and I'm going to, should get a number, kilopascals, that's right, 2 meters, 6.5 feet below the surface. So in this case, density is 1,000 kilograms per cubic meter. Delta Y equals about 2 meters, 6.5 feet. From here to my feet. Gives you exactly the same pressure change in water as from here a mile up gives you in air. And that's where the density of the fluid matters a whole lot on how the pressure changes. In fact, the density is the only parameter that really matters when you're talking about what these pressure changes are. That's right. So you're not experiencing drastically different pressures at these altitudes, but it's measurable. Sensitive pressure meters on your phone even can tell altitude differences between here and here by the pressure differences in the air. And that's a tiny bit. But when you get below the water, the pressure difference between here and here below the water is actually very substantial, noticeable.
So delta Y, like the H, like in the surface.
Yeah. This is delta Y. So this is a change in depth between the surface, or this is really any delta Y, right? Any delta Y will give you a pressure difference equivalent to 20 kilopascal in water. It doesn't matter where you are. If you start from the surface, you will increase by 20 kilopascals at about 2 meters below the surface. Any scuba divers in the audience, in the room, in the class? I'm not either. It's on my bucket list to learn how to become certified and do scuba. But scuba divers have to worry seriously about this. If you dive to 20 meters, 30 meters, 40 meters below the surface, the pressure is dramatically different than it is at the surface. You have to know exactly what you're doing in order for your body to be able to handle those pressure changes without causing really bad things to happen. So this is a very serious thing if you are planning to go to any depth down. Even swimming pools. I had a 10-foot deep, 12-foot deep swimming pool. Your ears will pop if you dive all the way down to the bottom because the pressure change from the top to the bottom is so dramatic. Okay, great. I've got 10 minutes left. And in that time, I can introduce another concept, which is pretty cool, which you've already seen kind of. Let's say we've already sort of seen the equation, right? Let's say I were to have I actually have this here. I have a fluid in this water bottle. It is at some depth, and there is atmospheric pressure pretty much at the surface of this water. What if I were to seal this up, put my thumb in it so that it were sealed, and press down on it? what would be happening to the pressure of the air inside of this cup? It would go up. What would happen to the pressure at the surface of this fluid? It would have to go up. What would happen to the pressure at this point in the fluid? It all has to go up. Right? If you change the pressure anywhere in the fluid, you change the pressure everywhere in the fluid. That is a statement known as Pascal's principle. He didn't get his name attached to this unit for nothing. He actually did some stuff. In an enclosed fluid, any change in pressure will occur everywhere in the fluid. No, the P is not the same everywhere. That's not to say, if I put my thumb down here and I increase the surface pressure, that all of the fluid elements are going to have the same pressure. They won't. It's still going to get higher as you go down. But however I increase the top, the pressure at the top is going to increase by the same amount at all other levels in the fluid. The delta P will be the same everywhere. If you change the pressure somewhere, that change in pressure will be felt by the entire fluid everywhere in the fluid. Okay, so for instance, if you push down on a plate, let's say you have some fluid. That's a terrible container that I just drew. And let's say this fluid is filled with water, and you push down on that plate, that will increase the pressure everywhere inside that fluid. And this actually helps us. How does this help us? P goes up everywhere in the fluid. So this can help us because we can build something called hydraulic levers. Hydraulic levers. How do hydraulic levers work? A car lift. Let's draw a. You can see my very poor drawing skills here. Here's my best car. Oh, that's a nice one. Okay, and let's say you've got some piston here that can raise or lower depending on, there's fluid inside this piston. And let's say that we've connected this to another piston, which has a much smaller circular area. Okay? Let's say that this has a radius of, I don't know, 20 centimeters. Let's just make some numbers up. And this has a radius of, let's say, half a centimeter. And let's say this car has a mass of 1,500 kilograms. I want to show you that you can build a hydraulic lever where it is quite easy for someone to push down on one side of this and have with very little force, and have a great deal of force applied to the other side, because the pressures involved change equally. So I know that the force down on the car, F car, is equal to just the mass times G. This is about 1,500 kilograms times, let's just keep the numbers round and call G 10 meters per second squared. This is about 15,000 newtons. And this up force must come from the pressure pushing on the plates inside this hydraulic lever. Okay? So we can calculate what pressure we need inside that fluid with that diameter plate to hold that car. Up force comes from pressure. The pressure in the shaft, if we're going to hold this car up, the pressure in the shaft must be equal to the force applied down from the car divided by the surface area of the shaft. We can write some numbers in here. I'm actually going to move this over here so I have some more room to work. Whoop. Oh, that's nice. Beautiful. This is going to be, we know what force is, that's 15,000 newtons divided by pi times 20 centimeters, or 0.2 meters squared. You do all that out, and you get about 120,000 pascals. About a little more than an atmosphere. Now, that's how much more it has to be, because obviously you've got the air pressure pushing down. That's a gauge pressure. That's how much more pressure has to be in the piston than is in the atmosphere. So really, the pressure in there has to be a little more than 2 atmospheres, absolute terms, in order for this to work. But we're going to have the same atmospheric pressure on the other side, so we can kind of ignore the atmospheric pressure for the purposes of this problem. It's going to be pushing in both directions, so we don't really have to worry about it. Okay, so we're going to call this is the shaft, and this is the piston. We know that whatever pressure is in the shaft must also be, whatever changes in pressure is happening in the shaft must also be happening in the piston. So the question is, how much the pressure there must also be 120,000 pascals. The question is, what force do we need to push down on that smaller plate to enact that pressure change, to hold the car up? Because the area is so much smaller, it's going to be a much smaller force. So PS, and this has to be equal to the pressure in the piston, which is the force that you exert on the piston divided by the area of the piston. So we can now solve for the force that we need to apply to the piston to keep this car up in the air. FP is AP times P, and PA is P shaft. This is pi times 1/2 centimeter squared. That's 0.005 meters quantity squared times 120,000 pascals. And we get, multiply those numbers together and square the 0.005, you get 9.4 newtons. So think about that. You can, if you have this hydraulic lever, have a 20 square centimeter radius, something like that, maybe, holding up a car, and on the other side you've got a 1 centimeter diameter, and all you need to do is put 1 kilogram of weight on gravity to hold up an entire car on the other side. It's kind of crazy to think about. You could, probably with your pinky, push down on the piston a little bit and raise a car on the other side. Now, is this magic? I mean, it seems like magic, but it's not really magic. It works pretty much the same way as levers do, which is what I call a hydraulic lever. You get the same kind of gains with a lever, right? You have a fulcrum here and a very short lever arm here and a very large lever arm there. You can apply a very small force here and get a very large force over here. And the same disadvantages with that system you get with this system, right? The total amount of fluid in this system is the same, is constant, And so you have to push down a very large distance on the piston to get a very small change in height in the car. It's very good at leveraging forces, but what you give up is distance. You have to push down, 10 meters over here to get a very small change in elevation over here. But it does work. You can have very small forces here, giving you very large forces over here, just by changing the surface area of the fluids of the plate. Okay, I'll stop there, and we'll come back to this on Friday. I think you have most of what you need for the homework, but it's not due for another week anyway. So, see you Friday. I forgot to do my concept question. Oh well. I'll do it next time.